Good afternoon, everyone. During this few minutes, I will be presenting our work entitled Scalable GPU-based decoding approach for massive MIMO technology. And as one of the main talk this morning pointed that one of the main 6 challenges for next generation communication network is to reduce the latency requirement for 5G and 6G. And this is exactly what we are doing here by leveraging high performance computing and accelerator. As predicted by Ericsson, by 2027, we will have like 40 billion connected devices from different technologies, from smart cities to self-driving cars and UAVs. And all these connected devices will exchange like a large amount of data. This will put like today's base station under huge burden and complexity. So one way to sustain this large number of connected devices and data exchange is to use massive MIMO technology. So massive MIMO is indeed one of the key enabling technology for next generation, but as of today, we didn't see it in action, in full action in industry. So instead of using just like one or few antenna to transmit and receive the data, we can use like 100. And this will increase all the potentials from classical MIMO in terms of diversity gain, spectral efficiency, and network reliability. And also this motivation, this massive MIMO is also motivated by the advent of nano antenna that can be integrated even in user cell phones. So I think the problem is not in the number of antenna that can be supported in base station. As of today, I think we can support up to 128 antenna in base station or even more. And we have also this trend of cell-free massive MIMO when we reduce like when we remove like the cellular decomposition. The mainly we keep the antenna there, but the base stations are removed and we use like centralized base station for all antennas. And here the number of antenna and number of users can increase very fast, especially in urban environment. So the number of antenna is not an issue. The real issue in massive MIMO technology is the detection and is the physical layers. And the main challenge is to provide scalable and accurate physical layers algorithm that can scale with the number of antenna. So for the physical layer, we are mainly like talking about channel estimation, signal detection, and the pre-coding, and having like accurate channel estimation and signal decoding is really important for massive MIMO to get all the benefit from it. And what we are interested here during this talk is the signal detection, because it is the most critical task. The performance of the network depends on it in terms of error rate and performance and accuracy. So this is what the main issue is. We need like new signal detection algorithm in order to sustain this large number of antenna. And why do we need that? Because in urban environment, when the number of user is very large and it is like close to the number of antenna, the performance of linear detection algorithm like zero forcing, MMSE, have very poor performance in terms of error rate. But still they are fast and they can be they can provide low latency requirement. So here we have like simulation for 100 user and 100 antenna in base station, and we can see that MMSE and zero forcing are not accurate even in high SNR regime. And the second issue about linear detection algorithm is the scalability. So this algorithm, linear detection algorithm involves matrix inversion operation, which is computational demanding. The second option to provide like signal detection is to solve like massive MIMO optimization problem, and which is very challenging. So the first equation here is like the traditional MIMO equation, where Y represent the observation from different antenna. We have the channel matrix H, and we have the transmitted vector, and we have the noise vector as well. And what we are trying to reach here is a solution that minimize the distance from the observations and the received signal. This problem can be cast to another minimization problem by performing the query decomposition. So this is very complex, discrete optimization problem because the number of possible solutions increases in exponential way. For instance, if we have like 64 QAM modulation and 100 antenna, number of possible solutions is 64 power 100. And targeting the maximum likelihood and the optimal solution in very low latency is extremely challenging. So we have the optimal approach like sphere decoder and maximum likelihood solution that explore the whole search tree and provide proof of optimality. They are very accurate, but they are not usable like for massive MIMO. Mainly we can use them like for couple antenna, but they cannot scale beyond. We have also approximate approach, which are based on sphere decoder that perform like trade-off between the complexity and the performance. But still, when we scan the number of antenna, we cannot use this approach for under the real-time requirement. What we are trying to achieve here is to use like accelerator and GPUs in order to sustain the following goals, like having low latency. Ideally here is to have the same latency as linear detection algorithm. And this is mainly by exploiting GPUs. So GPUs is just like a phone that can be integrated like in base station without having like major change. And it will provide like a huge computing power that can be used for different applications, as well as for edge computing and supporting a large number of edge applications. And we are trying to achieve like near optimal error rate by targeting the maximum likelihood solution. And this is mainly by proposing new algorithms. So achieving high data rate by supporting dense constellation and massive number of antenna, and trying to reduce the energy consumption by relying on energy efficient architecture. And accelerators are known to be very efficient, and they will not like increase the power budget of the base station. And as of today, we were pretty much successful and to support up to 400 by 400 antenna under 10 millisecond latency requirement at practical SNR of 20 dB. So what we are not like the first to propose like high performance or parallel approach that exploits high performance computing architecture. There is several approaches that exploit GPUs, FPGAs, multi-core CPUs, but the mainly these approaches are not scalable, cannot scale beyond like 30 antenna, and they have very high latency because they are based on like partial exploration of the search tree, and they are very irregular. What we proposed here is to propose an algorithm named like multi-level approach that combine the detection of multiple symbols together. So here we cast this process as matrix algebra operation, and we leverage the GPU in order to stay within like practical time complexity. So in our algorithm, we are not managing a large number of data structure. We have only one solution that we empty initially, that we extended at each iteration with several symbols until reaching a complete solution. And this process is casted at matrix multiplication. And the interesting fact is the more combined, the more symbols we combine together, the better the accuracy is. And this will avoid like error propagation, because if we get the first symbol wrong, most of the time the following symbol will be detected wrong as well. We implemented our algorithm to avoid redundancy in computation, and even for this non-computed part, we provided it in 2 steps model in order to avoid like communication between CPU and GPU. And this communication between the central processing unit CPU and the acceleration is the performance killer. So we need like to avoid it as much as possible. So we divided like the evaluation process as 2 steps, as matrix multiplication and matrix vector multiplication. And as I said, in our approach at each iteration, we use like 2 main steps. The two main steps. The first one is matrix multiplication, and second step is to do sorting and reduction process. And if we can see here that the matrix multiplication consume like 80% of the execution time, and the reduction process and sorting consume like 20%. So we need to do something here for the matrix multiplication in order to reduce its size. So the first thing we did is to exploit lower precision mode in the computation. So for instance, for voice communication, mainly we use like single complex in order to do the computation. So what we did here is to exploit even lower, even half precision mode. And what we get is we got two times improvement in terms of latency without having like without sacrificing the accuracy. Is it the same error rate performance by using single precision or using half precision? We got the same accuracy. Second interesting fact about our algorithm is that the multiplication that we do at each iteration can be overlapped in all iterations. So we can do the multiplication at all iterations just once. And then the norm and sorting phases can be done sequentially. So here is the performance results about our approach. And as compared to the Optimus with the decoder results.
We're running a little behind. Would you mind wrapping up your talk, please?
Okay, so I'll try to go fast. So here we can see that the more levels that we combine together, the better the accuracy. And even with 4 and 5 levels combined, we are close to the performance of the maximum of the sphere decoder approach. And here we have we have like in subfigure B, we have the complexity, we have fixed complexity through SNR, and we have like huge gap in terms of complexity as compared to sphere decoder. And number of combined levels here can be adjusted according to the trade-off between latency and accuracy that we want to achieve. And here is the number of antennas that can be supported by our approach under the 1 millisecond latency. And what is interesting here that our approach has linear increase. If we can see the brown curve here, which is for MMSE, we can see that the MMSE curve increases, don't increase in linear fashion. And starting from 300 antenna, our approach is even has better latency than MMSE algorithm. And if we can see the throughput as multiplication of the number of antennas that can be supported, we can see that our approach can achieve up to 4x improvement as compared to the MMSE algorithm. So here is comparison between GPU and CPU results. And just by going from CPU to GPU, we have like 2 orders of magnitude. This is the red bar, 2 orders of magnitude higher speed up just by going from CPU to GPU. So by exploiting the half precision mode without sacrificing the error rate performance, we increased the performance up to 166 times faster. And by exploiting multiple GPUs in base station, we can support up to 300x. And this is really important to achieve low latency for next generation communication network. So this is error rates and performance results for our approach using different modulation. And as we can see also and mention, the linear detection algorithm are not performing well in this case when the number of antenna is equal to number of users, which is pretty much realistic in real scenarios. And here showing the throughput, you can see that our approach can have 8 times better throughput as compared to the MMSE. So to conclude is the importance of using high-performance architecture in base station in order to support various application and also to reduce the latency for next generation communication network. And our approach can support up to 400 antenna in massive MIMO environment under the 10 millisecond latency. And thank you for your time.